Good morning, this is Ashokan from RealNet Labs Private Limited. Let us discuss cryptography today. Cryptography is the science of secret writing. What do we mean by secret? Secret means one person or a group of people. This one person has to talk to other person or a group of people. The communication should be from within a group of people. This should not be known to any other third person. And this particular communication, if somebody catch hold of the data in between, he should not be able to read and understand. This is what secret means. If you want to encrypt this message, there must be two things required. One is an algorithm, another one is the key. The algorithm is a mathematical function or it is an equation, and the key tells how to carry out the mathematical functions. For example, there are a lot of functions, function 1, function 2, function 3, function 4, and about 30 functions are there. But the key which tells that you carry out the function 1, function 8, function 7, function 2, function like that. So how to carry out the mathematical equations, in what order, that is what the key says. So the key is important and the key is secret here, and the algorithm is not secret. The algorithm is open, it's not secret, but key is secret. Let's take an example here. I have written here A to Z, the English alphabets, A, B, C, D, and this is equivalent to an algorithm. This is not a secret, so we can say this is an algorithm. And the key is secret. Let's say it is 2. The key is 2. Let us take an example. The key is 2. In that case, I have a word, say Sam, and if I want to encrypt this particular message or make this English plain text as unreadable format or create a cipher text, then I have to apply this key based on this algorithm on this message, which means S becomes C, S becomes what? S. Key is 2, that is 1 and 2, S becomes U. Like that, A becomes B and C, like M becomes N and O. So if the key is 2, that means the S becomes U, S becomes U, A becomes C, and here M becomes O. So this is what is known as the cipher text. The UCO is a cipher text which is going through the wire to the destination, and at the destination it receives as UCO. Then the destination person must have the same key which is used to encrypt a message. This destination person also must have this particular key in order to make this cipher text into a plain unreadable text. And when he applies this, what happens? U becomes 1 to S, U becomes S, and C becomes A, and O becomes M. So he gets the plain text here. And if at all somebody catch hold of this data onto the wire, he will not be able to read and understand this because he does not have this secret key with him. Let's understand what is a crypto system. The crypto system is something known as an implementation of the cryptography, which transforms a message from plain text to cipher text. Let us understand what is this plain text and a cipher text. A plain text means it is a readable format. Plain text means it's a readable format. If I say the plain text is Sam and something X, Y, Z is the scrambled, when you do some process here, the process creates this particular result of this particular message, then this process is known as encryption. This is plain text and this is cipher text. This is known as plain text. This is cipher text. And through this encryption process, you can create a plain text into a cipher text or an unreadable format text. What is cryptanalysis? The cryptosystems cryptosystem is in total, that is what is that it includes. It includes that key and it includes that algorithm and the protocols and softwares. All it's together, entire thing is known as the cryptosystem. In totality, it's known as a cryptosystem. Cryptanalysis is the practice of obtaining the plain text from a cipher text, breaking the encryption. This is breaking the code. If somebody is breaking the code, or it is violating the authentication schemes and decoding something without the permission, or decoding the secrets, such acts are known as the cryptanalysis. So the cryptanalysis is the practice of obtaining the plain text somehow from the cipher text by breaking the encryption or breaking the code. And let us look back to Caesar cipher. This is rather old one, and there is the terminology symmetric. Symmetric means it is similar. Symmetric means it is similar. We are going to discuss down what is symmetric and asymmetric cryptography. Let's understand. The similarity is the sender and the receiver use the same key. The sender and receiver use the same key. Here also, the previous example, if you take this key is 2 and the key is used to encrypt a message here, the same key is used to decrypt that message. So the similar means the key is similar. The key which is used to encrypt a message, the key which is used to decrypt the message is one and the same. That is where we say the symmetric. So here the Caesar cipher, the key is 3 space in the alphabet. 3 space in the alphabet. Since A, B, C, D, this is the English alphabets. If you see this shift, it shifted 3. A, B, C, D is the first letter, E and F and G, H, it goes like that till after the Z, A and B, C comes there. This is what the cipher. So if you want to encrypt a message says Sam, that means S becomes what? S becomes V. So V and A becomes D and M becomes what? M becomes P. So VDP is the secret. But this is not much deep for anyone to figure it out. But we should remember that this was there at a period where there were not much people to read and understand the text. Another one is the substitution cipher. Substitution cipher substitute. It replace each letter in the plain text with another. Each letter it will be replacing with another one. So the alphabet is A, B, C, D, E, F, G, H up to Z. And this is the opposite, the reverse wise. ZY is W, V, U, T, S, R, Q, P, N, M, L, K, J, H, I, G, F, E, D, C, B, A. It comes like that. So if the same word, if you want to say for example Sam, the same Sam, if you are encrypting here with the substitution, you have to, the S will be substituted with another letter H. So S becomes H and the A becomes Z and the M becomes N. So H, Z, N, this is what the cipher text, and if you have the same key, you can reverse it, the same thing. It's not much deal. But this is what substitution cipher. The Caesar cipher is shifting the alphabets and the key is secret here. The substitution, it is substituting. And the next one is polyalphabetic cipher. In the polyalphabetic cipher, each row corresponds to a cipher. We have a table here, and if you see each table A, B, C, D, that means it's a shift 1 in the alphabet. It's each and every column, every row corresponds to a Caesar cipher. The first row shift 0, the second row shift 1, and so on. The last row shift 25, like that. With this table we can encrypt the data, provided we need to have a secret key. The key is secret. That's how it works. It works like, for example, if you have a say key secret, S-E-C-R-E-T, this is what the secret, and the secret key will be written like again and again, S-E-C-R-E-T, S-E-C-R-E-T, like that. Now if you have a plain text that my bank PIN number is 1234, you will append the letter like this: my bank PIN number is 1234, something like that. Now you have to find out the cipher text. The cipher text is, the first letter is S here and the intersection is M, S and M. If you go to the S here at the S here, this is where the S is, this is where the S is, that's the secret. And now if you come down, the letter is M, you need to find the letter M in this particular row. There is M here, there is M here, and from this M you need to find out what is that intersecting point. The intersecting point is E here, the intersecting point is E, so the E is the cipher text for that. E is the cipher text for that. Similarly, E and Y, if you go to E and Y, E is the cipher. E, you'll have to find out where E is, and you'll have to find out where Y is. Here it is Y, and the intersection of this Y and E, it is C, and C is the cipher text for that, and here C is the cipher text. So E, C, like that you have to do. Using this particular table, if you change this particular secret key, then everything will change. It is not that easy to figure it out. This is what a polyalphabetic cipher, and using this table you can do the encryption. The next one is the transposition cipher. Transposition means it transposes, it changes, it's like a jumble puzzle. And here there is a message real net lab, and the message is grouped into REALNET, so 1 2 3 4 5, 1 2 3 4 5, it's grouped like that, and there is a key 24153, and this jumbled sentence has to be arranged according to this particular key. That means 2 is E and 4 is L and say 1 is R, like that. So 2 is E and 4 is L and 1 is R. So this is what the cipher text. You have a message, this is a plain text message, and this message is grouped in such a fashion, and there is a key, and the key, when it is applied on this message, and we will get this cipher text, and this cipher text has to be again replaced with this key. So this is what is the transpose or the transposition ciphers. Let us go to cryptosystems. The cryptosystems, there are two types of cryptosystems mainly, the symmetric and asymmetric cryptography. Symmetric means it is similar. Symmetric means it is similar. Asymmetric means it is not similar. Symmetric means it is similar. Asymmetric is not similar. So let us discuss the symmetric cryptography. The traditional form of cryptography known as single key, secret key, or symmetric key, any name you can call. Single key cryptography or secret key cryptography. And this symmetric key uses the substitution and transposition techniques to encrypt the message. The process of encryption is that there is a plain text and it is encrypted, and you will get the cipher text. The plain text is readable and the cipher text is unreadable. And when you give this to the recipient, this you send to the other person, the other person will have the cipher text. He will decrypt it using the same key, and he'll get the plain text. Let us understand the process here. If at all, say A wanted to talk to B, and A takes a plain text message, this is a plain text message, and he uses a key to encrypt the message, so he'll get the encrypted message. This is known as a ciphertext, and this is plain text. When A sent this encrypted message to B, B receives the encrypted message. B received the encrypted message, and here the same key should be there for B to decrypt the message. So the same key is transmitted to him, so that B also got the key there, and when he applies this key on this encrypted message, it does the reverse action. So you have the plain text message here. You can read and understand. So the similarity or the symmetry means the key which is used to encrypt a message and the key which is used to decrypt a message is one and the same. That means if at all somebody wanted to communicate with different people, A want to communicate with B, which means he has to create an AB session key, and the same AB key has to be given here. If this person wanted to talk to C, then AC and AC, the key has to be given here. If by mistake this AB key is given here, the message which you send by inadvertently, if you send the message to him, he'll be able to read and understand. So the difficulties are that you have to, if you want to communicate with 500 different people, 500 different keys you need to maintain here. So the key maintenance is the difficulty. Key maintenance is difficult. And second key, the key has to be transmitted through a secure channel. You don't have a secure channel, you cannot send it by email. It requires a secure channel. So key distribution is the difficulty. One is the key maintenance, and the second is the key distribution. These are the two difficulties with the symmetric cryptography, but it is faster than asymmetric cryptography. So let us understand what is brute force attack. Brute force means trying all the possible combinations to break an algorithm, break a code. So it's also known as the exhaustive search attack. Exhaustive search attack. If you have you remember the suitcase with a key lock. If there are two numbers, the number key lock, if you try 00 and 99 up to 99 up to 100, try, if you give, you can break this. If it is 000, one more 0, it is 1000 times. So the key is, as the key size is increasing, and you will have difficulties here. So the exhaustive search attack is the trying all the possibilities to break the code. That is what something known as a brute force attack. Let's understand the symmetric algorithm. Here we have understood what is symmetric key. Symmetric means it is similar. Symmetric means it is similar, and the key which is used to encrypt a message, the key which is used to decrypt the message is one and the same. And the key maintenance and the key distribution are the two difficulties in the symmetric key. Let us understand the various algorithms here. The encryption algorithm can be applied on plain text message in two different modes. The symmetric, there are two different modes. One is the block cipher, another one is the stream ciphers. One is the block cipher, another one is the stream ciphers. Block ciphers means if you take a message and you cut it into different blocks here, block number 1, and you have another block number 2 here. This is block 2, and another one is block 3. If you have different blocks like this, when you encrypt this particular data, what happens? You will get the cipher text here. This is what the cipher for block 1, and this is for the cipher for block 2, and this is for the cipher for the block 3. Now when you encrypt the data, you get the ciphers like this. But here the problem is, if the block 1 and block 3 are identical, if this block 1 and block 3 are identical, you will get an identical cipher here. So from this identical cipher, there are patterns which gives to the hackers that you can deduce the original message. So this is what the block ciphers. And data encryption standard is DES. It is a block cipher data encryption standard, and it does 16 rounds of mathematical procedures to get the plain text into the ciphertext. Before it gets the plain text, before the plain text becomes the ciphertext, there are 16 rounds of mathematical calculations of procedures which is going in between. So that is how the DES work, data encryption standard. So let's understand a little bit about DES. DES is a data encryption standard. In 1974, the NIST, the National Institute of Standards and Technology, with the NSA, National Security Agency, they have invited algorithms for a standard, DES. DES is not an algorithm, it's a standard, and so many people have given their algorithm, and IBM has given their own developed algorithm called Lucifer. So the algorithm which is used in this particular standard is known as Lucifer. This is what the algorithm. Basically it was 128-bit, but NSA has reduced this to 64-bit. And again, this 64-bit includes 8-bit of parity, 8 parity bit, and in total it is 56 bits. So DES is 56 bits, and this refined thing is known as DEA, data encryption algorithm, and DES is the standard. There are various modes for the DES: CFB, OFB, ECB, and CBC. The first one, the CFB and OFB, that is the cipher feedback and output feedback mode. This is implemented in softwares because these are stream ciphers. These are stream ciphers. We have discussed that there are two things. One is the block cipher and the stream ciphers. Stream ciphers we will discuss now. The cipher feedback and output feedback too are stream ciphers which are used in hardware. Whereas the ECB and CBC, these are block ciphers, this used in the software mainly. So these are the various modes of that. And triple DES, 3DES, triple DES, there is another mode. Triple DES can do 3 rounds of encryption with either 2 keys or 3 keys. Let us understand what is this 2 keys and 3 keys. If the encryption is based on 3 keys, it encrypts with 3 keys. For example, if you have say an algorithm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and encrypt with 3 keys. This is key number 1 will have, say, key number is 1 is 2, 1 is 4, and 1 is 1. That means this is the key length, the key sizes, which means that first is 2, so the encryption will happen like this. That is 2 keys apart, then 4 keys apart, 1, 2, 3, 4 keys apart, then 1 key. So the key length of this and this is different. This is what the encryption. And encryption, decryption, this is the same thing, 1 and 2. If you say the encryption, decryption and encryption is within the key size, a different key size, encrypting with 1 key, decrypting with another key, encrypting with with another key. That means the key could be say 4, 2 and say 3. That means 4 means you will encrypt the data with 4 keys. Encrypt the data with 4 keys, which means that from 1, 2, 3, 4 it goes to 5, and again it is decrypted with 2 keys. That means 1 and 2. It's a different. So 1 is the plain text which is being converted into 5, and this is ciphertext. Again the next encryption also gives the security that this is also ciphertext. Then again you will encrypt with the 3. That means it is a ciphertext. All the ciphers. So 3 triple encryption it gives. That is encryption, decryption. The same thing you can do with 2 keys also. 2 keys also, because if it is 4 and 2, you can say 1, 2 and 3. The key size is same like that. Or first key is 4, a second key is 2, third key is 4. So this key length is 4, this key length is 4. So these are one key, and this is a different key, the second key. So with the key 1 and 2, two different keys, you can do the triple dash. So these are the various modes of triple dash. Now let's understand what is advanced encryption standard. The NIST has developed the advanced encryption standard to replace the DES. DES was obsolete, so it was trying to create a new algorithm, that is AES. AES stands for Advanced Encryption Standard. The AES is AES-X. The X stands for the bit size. It is 128 bits, 192 bits and 256 bits. Various, it gives much different strengths. So AES 128, AES 192 and AES 256. And the number of rounds and the iterations of the main algorithm can vary, depends on maybe 10 to 14 different iterations based on the block size and the key length, and the block size. So this is the block cipher, and the other block ciphers are triple dash, two fish and blowfish, RC4, RC5 and 6 and 7. So many algorithms are there, including this international data encryption algorithm. This is known as IDEA, International Data Encryption Standard, which is again a block cipher with 64-bit block size, and the key length is 128. Now let's understand the CBC mode. CBC means cyber block chaining. CBC stands for cipher blockchain. We have already seen the ciphers. When it is block 1 is encrypted, you get a cipher, and block 2 is encrypted, you get this block size is the block size of this plain text, and the block size of the encrypted is one and the same. And if the block is the same text here and here, the cipher also will be the same, and you can't do anything about it. This is what the block ciphers. But the chaining means you can chain the block ciphers. So how to chain the block ciphers we will see. When there is a block 1 and block 2 and block 3 like this, block 1, block 2 and block 3, before the encryption we introduce something known as IV. IV stands for in-train vector. When the IV is introduced here, the IV plus this particular block is encrypted, you get a ciphertext 1 here. And here the same IV, if you introduce here, then encrypted this, again it doesn't make any difference between the previous block cipher and the cipher. And the IV has to be introduced in each and every block. It's very difficult and cumbersome, and the IV cannot be repeated here. Instead of this, what the CBC does is that when a block is taken and an interim vector is introduced to that and it is encrypted, you get the cipher block 1 here, and this particular cipher block will be fed to as an interim vector for the second block. and the second block is encrypted, you get a ciphertext here. This is again is the IV for the third block. So this is what is known as chaining. Cipher block chaining. So when it is chained, the end of last block cipher, this is what the cipher of that particular text, and when it is reversed, you get this particular text back. So cipher block chaining is introduction of an interim vector, and the result of the first cipher will be fed as an IV for the other one, and it is chaining like this. This is how the cipher block chaining works. And the stream ciphers operates on bits. It is not operates on a block. It operates on bits, and it generates a key stream. How does it work? The stream ciphers generates a key stream, and this key is combined with the plain text here, and an XOR operation is carried out so that you get the ciphertext. It's a simple binary arithmetic, and two identical bits. The rule is the two identical bits gives 0, and two different bits is 1. For example, if you see this, this is different, you get a 1, and two identical bits get 0. Two identical bits get a 0. See here, two identical bits get a 0. This is what the XOR operation. Once the key stream is created by the cipher stream, plain text is fed, and you get the ciphertext once the XOR operation is created. This is what it is. The key stream is XORed with the plain text. You get the ciphertext here. Now let's move into asymmetric cryptography. Asymmetric cryptography, it's not like symmetric cryptography. It is each user has a public key and private key combination. Each and every user will have a pair of and it is asymmetric is otherwise known as public key cryptography. It is introduced in 1976 by Diffie and Hellman, Whitefield Diffie and Martin Hellman. Let's understand what is the algorithms. The algorithms are Diffie-Hellman algorithm, and the Diffie-Hellman algorithm doesn't do any encryption. It is a key agreement protocol. It is a key agreement protocol. Let us understand, before going to the algorithms, what is this key pair. The key pairs are the public key and a private key. Each user will have a public key and a private key. For example, A wanted to talk to B, or they would like to do some secure communication, which means that the public key of A can be publicly given to anyone, or it can be published in any CAs or directories or even websites. This is what my public key. And the private key of A will be there with the owner. That should not be given to anyone else. This is very important. And B also keeps the public key of B is also publicly given, and the private key of B is with the B only, with the owner. It should not be. This is highly secret, and this is not secret. The public key is published, and when the encryption is taking place, if you take a plain text message, you can use the key. Now, what key can be used to encrypt the data? The difficulty in understanding this private key and public key is that we need to understand the private key and the public key are mathematically related. This public key and the private key are mathematically related, and the private key for this particular encryption here, you can either use the private key or you can use the public key. The private key can encrypt, the public key also can encrypt. Both the keys have the capability of encrypting and decrypting. The crux of the matter is that which key you will use for what purpose and when. That's what it is. But one thing we need to understand is that if you use a private key to encrypt a message, only the corresponding public key can decrypt it. If you are using this particular private key to encrypt a message, only the corresponding public key can decrypt it, not any other public key. This is very important to understand. In most of the literature, if you read that, you will read that private key can be used for encryption, public key can be for decryption, fine. But if you change that into a private key, if you use for encryption, and only the corresponding public key can decrypt it, things will be much more easier for you to understand. It's very easy. We will discuss this, and let us understand this algorithm first. Diffie-Hellman is a key agreement protocol, which means that we will come back to this exercise again. Diffie-Hellman is a key agreement protocol, which means the public key can be transmitted. A's public key can be given. A public key is here. This can be given to B. B's public key is here. He can be given to A. So if at all the keys are exchanged, after the keys are exchanged, the public keys are exchanged, what happens in the Diffie-Hellman? The private key of A and public key of B, it creates a session key for a particular session here in this machine itself. Similarly, the private key of B and the public key of A, this particular combination creates another session key here, and this session key is used as the key material for encryption and decryption. So using this key, if you encrypt, it can very well decrypt it with this particular key, because it's also created by this. So Diffie-Hellman creates this session key, and these session keys are not transmitted. So man in the middle attack is not possible here. But Diffie-Hellman is vulnerable for man in the middle attack if, in case, when the public key is given to him initially, when there is no authentication provided here, if the authentication is not provided at that particular place, then an intruder can come and he can give his public key saying that this is the public key of A. There the man in the middle attack is possible. So next one is the RSA. RSA is, this is Ron Drivers, Nadi Shamir and Renaud Edelman. This is the first name of the first letter of the surname of the creators, R, S and A. Sorry. RSA. RSA is a very strong algorithm, and it's a public key crypto system developed in 1977. In 1977 it developed by Ron Drivers, Nadi Shamir and Edelman, that offers both the encryption and digital signature, that is the authentication. Okay, as I told you, RSA stands for the first letter in each of its inventors' surname. The security of the RSA is based on the assumption of the difficulty in factoring. That is based on this, the RSA work. Next one is the LGAML. LGAML is also a public key system. It is based on discrete logarithms. Discrete log. It allows both encryption and digital signature services. It is important that what security services gives by the symmetric and the asymmetric. The asymmetric cryptography we are discussing because it gives the full range of security services, which we are going to see in a minute. And LGAML is an extension of the Diffie-Hellman key exchange protocol. Diffie-Hellman will not have the capability to encrypt, whereas the LGAML has the capability to encrypt the data. Encryption. Another is the ECC, elliptical curve crypto system, which we are going to discuss in another class. Let's understand what are the advantages of symmetric key in the asymmetric. In the symmetric key system, the symmetric key algorithm, The key distribution was the problem. So here it's not a problem because you can always publicly publicize this public key of a person. It is scalable because if at all 2000 people have to communicate, they need to create very less key, only a key pair for. If one person has a private key and a public key, he can communicate with the n number of people. He can give the public key to anybody, and he has to keep the private key with him and the public key to any person. And it provides a range of security services. So the advantages of asymmetric cryptography is that the key distribution is very easy, and the scalability is there, and it provides a range of security services. And this we will discuss down. And let us understand what are the features of the public key cryptography. The features among this: privacy and confidentiality. A communication must have a privacy and confidentiality if it wants to be secure. And the authentication must be there, data integrity must be there, non-repudiation must be there. So in cryptography, we have answer for all this. In cryptography, we have answer for all this. The privacy and confidentiality can be achieved by encryption. And the authentication can be achieved by digital signature. Digital signature. Or you can have the CA certificate also. And the data integrity is achieved by something known as hashing. Hashing and creating a message digest. And the non-repudiation. Repudiating means denying. Non-repudiation. This is also achieved by digital signature. So there is a concept PKI. PKI stands for Public Key Infrastructure, which provides the full range of security services. What are the full ranges? The ranges are the privacy, it can give the confidentiality, it should give the authentication, it should give the data integrity, because if one sends some data from one place to another, the data integrity says that for the data integrity, if one send a message that use maybe say for example 100 rupees from here, and when it reaches here it should not be 10 or say 10,000. It should not be like that. If at all somebody tampered the data in between, this can happen. If this happens, there should be some mechanism for the recipient to understand the data is tampered, and that is what the data integrity is all about. Let us discuss this. The PKI is public key infrastructure. I told you this provides the full range of security services, and it consists of a public key and a private key, a digital signature, digital certificates, a hashing, and the message digest, and there are a lot of other things also along with this. Means there is a CA, that's a certificate authority who issues the certificate, and there is something known as registration authority, the certificate authority that issues the certificate to the individuals. The RA verifies it. The registration authority is verifying, it's a verifier of the authority before the digital certificate is issued. And there will be a lot of directories where the certificate with the public keys are held, and there is a certification management program. All these, the public key, private key, digital signatures, and the certificate, all these combined together is the PKI infrastructure. So with public key infrastructure, how to provide the full range of security services, let's understand. Let us take an example of say two people, say Sam and Thomas. Sam and Thomas, they would like to communicate securely. So the public key of Sam and the public key of Thomas are published. This is no secret at all. the private key of Sam is there with Sam, and the private key of Thomas is there with. So this private key of Sam and the public key of Sam are mathematically related in such a way that what one key does, this will undo it. What this will do, this will undo it. Similarly, the private key of Thomas and the public key of Thomas are mathematically related. This is the key pair. Every person, every individual user must have this key pair. Now, if Sam is taking a message, a plain text message, and he wants to send this confidentially to Thomas. If he wants to send it confidentially to Thomas, then what he has to use is, he has to use the recipient's public key to encrypt the message, which means the public key of Thomas has to be used to encrypt the message. If public key of Thomas is used to encrypt a message and create the encrypted message, this encrypted message can be given to Thomas, can be sent to Thomas. This is encrypted message given to the Thomas, and the corresponding opposite key, public key of Thomas, is used to encrypt the message. The corresponding opposite key is the private key of Thomas, which is there with Thomas only, and Thomas uses this private key to decrypt the message. Private key of Thomas, it is there with him, and he can get the plain text message, which means that any key which is used to encrypt a message, the opposite key can decrypt the message. But now the problem is, why can't we use Sam's own key? Let us understand that. If Sam is using instead, if this particular Sam, after using the public key of Thomas, he created this encrypted text, and this text is given to 1,000 other people. This 1,000 individual will not be able to read and understand because they do not have this private key with them. So what we achieve here is confidentiality. So confidentiality is achieved here by using the public key of the recipient. If at all one wants to send a message to another person, the recipient's public key is used to encrypt the message. Instead, the same plain text message, if the Sam used this private key to encrypt a message, that will encrypt. If he used the private key of Sam, still you will get the encrypted message. And if you send this to 1,000 other people, all the 1,000 other people will be able to read and understand, because what you used here is the private key of Sam. The opposite key is the public key of Sam, which is available easily in the internet, or it is public. It is no secret. When it sends to 1,000 other people, all the 1,000 other people can catch hold of this public key, that is the opposite key of the key which is used to encrypt. So confidentiality cannot be achieved here, which means essentially that if at all you want to achieve the confidentiality, then you have to use the public key of the recipient to encrypt the message, because the other key will be there only with the owner, and he should not compromise that. Once he compromises, it's a difficult issue, a different issue altogether. Supposing that the Thomas is a bank manager. He is a bank manager, and this particular plain text message says that you transfer rupees 10 lakhs to, say, Ashokan's account. You transfer rupees 10 lakhs to Ashokan's account. That is what the message in this plain text message. And he got it. He used his private key to decrypt this particular message, and he got the plain text. This plain text says that you transfer rupees 10 lakhs to Ashokan's account, and he did that. After transferring the 10 lakhs, Thomas is calling Sam and say that I have seen your mail, I transferred rupees 10 lakhs to Ashokan's account, and what Sam says is that I never sent a message like that. He denies that I never sent a message like that. So the message came here confidentially, but Thomas used his own private key and he got the message, but there is no mechanism for Thomas at this point of time to say that it has come from Sam only. It came confidentially, fine, but how you can ensure that it came from Sam? Instead, suppose there is a hacker Ashokan, and he created this message, wanted to purposefully send rupees 10 lakhs to Ashokan's account, Sam. He created this message. He can also get the public key of Thomas because it is publicly available. He can also get it from the public, and he encrypt this particular message. He encrypt the public key of Thomas, and he could have sent this message here. If he sent the message, Thomas will believe that it is coming from Sam, but it is coming from a different person. In that case, if he transfers it and call this fellow, and Sam will be innocent in that case. So this is possible. And how do we make sure the authentication part of it? Let's see. A plain text message is taken by Sam and it is encrypted with the public key of Thomas, and it is encrypted. This is what the encrypted message. Now after doing this, what Sam does is Sam does the same thing, the same plain text message, and he runs a hashing algorithm. He hash it. The hashing algorithms are MD5, MD4, message digest 4, message digest 5, and SHA-1 and SHA-128, 256, SHA-128, SHA-256. All these are hashing algorithms. Hashing algorithms. When you hash it, what happens? You get something known as a message digest. You take a plain text message and you hash it. When you hash it, you get something known as message digest. Let's just understand something about this message digest in the hashing business, then come back to this area. Hashing algorithms are MD4, MD5, SHA-1, 256, 384, 512 are the digest bits. 160 bit digest SHA-1, it is 256 bits digest and 384 bit, and this is 512 bit. That you get a message. The hashing algorithm has various characteristics. When you take a plain text message and hash it, you get a message digest. Nothing happens to this plain text. It is as such is there. But the plain text message digest will be, you are getting this particular message digest of that plain text. And it is one-way hash. It is one-way hash. One-way hash means once you hashed it, you get a message digest. From this particular message digest, there is no way to deduce this plain text. You will not get it. It is not the reverse. It is one way. That's what is one-way hash. And it's constant in size. Constant in size means, suppose if you use a SHA-1, 160 bit size is the digest. That means a 10 KB message, if you take and hash it, you get a same constant size, and 100 KB message, if you take, you get the constant size. And if it is 1000 KB message, if you take 1000 KB message, the size of the message digest will be one and the same. That is what the constant in size. This is one characteristic of the message digest. Now there is a small variation in the source results in very large variation in the destination. Means if at all you send a plain text, this is a plain text, you take a digest and both you send to someone, and before it reaches here, and this particular person got this plain text and a message digest. Message digest. And in between, somebody catch hold of the data. he tampered this particular data, and when he sent this particular data here, you run a hashing algorithm here. Similarly, with this plain text, the recipient run a hashing algorithm. He creates his own message digest. He compares this message digest with this message digest. This was originally created by the person who sent at the source, and this must be the same. And if this plain text is not tampered, this and this must be the same. When it is compared, then the which can make sure that the data is not tampered. If it is not compared, that means the message digest is message is tampered. If the message is tampered, then when you hash it, you get a totally different message digest, which will not tally with this. So if it is not the same, that means data is tampered. So the hashing, as it is one-way hash, it's a constant in size. The result of the message digest is constant in size, and the variation in the source, a small variation in the source, will result in a very large variation at the destination. This is what they have. So we'll come back to this. Here the plain text message, the plain text message is there. Running a hashing algorithm will create a message digest. This is a chunk of data, and this particular chunk of data is taken by Sam, and he encrypt this with his own private key of Sam, and he creates something known as digital signature. When you use your private key on any message, that means you essentially produce your digital signature. When you create your digital signature, you use your private key, and this particular message is, this message digest is encrypted using the private key of Sam. That means the opposite key of the private key is the public key of Sam, that will be used to decrypt the message digest, digital signature. This digital signature can be decrypted using the public key of Sam, because this is the opposite key of the key which is used to encrypt this message. Now this public key is publicly available, so anyone can use that onto this digital signature. Now what he does, he takes there is something known as a hybrid also. Public key cryptography, if you use the public key to encrypt a message, it is very intensive computing resources it will take. So you can create a secret key or a symmetric key also. So what Sam does is, he takes a plain text message, he creates his own secret key, and he creates the message encrypted, this encrypted message, and he now creates an envelope. He creates an envelope now, the digital envelope he creates, putting all this together, and in this digital envelope, the particular plain text or this encrypted message could be there, encrypted message, and the secret key also you can put, because the secure channel you can send it to the other person, and the digital signature also is added here, the digital signature, and if it is required you can create this message digest also, because once you decrypt the digital signature, you are going to get the message digest, it doesn't matter, but if it is required you can message digest also you can include in this. So let me include the message digest also here, and this particular envelope has to be encrypted. This has to be sent to whom? This has to be sent to Thomas. So Thomas is the recipient, and confidentiality should be achieved. That means the public key of Thomas or public key of the recipient has to be used to encrypt this particular envelope. So I'm using the public key of the recipient, the public key of Thomas, and you got the encrypted message, and this message is being sent to Thomas. This message is being sent to Thomas. Now what happens? Thomas received that encrypted message. This is what the digital envelope sent by Sam, and it has a lot of material. Once you decrypt it with your own private key of Thomas, you see what is there inside. What is there inside? First is a encrypted message, and second is the secret key, and third one is the digital signature, and the fourth one is the message digest. These four, encrypted message and symmetric key and digital signature and message digest, these four have been extracted. All these four have been extracted from this digital envelope by Thomas using his own private key, because this envelope was encrypted with the public key of Thomas. So the corresponding private key is used to decrypt it. Now what he does, he used this. See, the secret key also has been sent to Thomas in a secure channel. This is what the secure channel, and he applies this key on this encrypted message, so it is getting decrypted. The plain text message says that transfer rupees 10 lakhs to Ashokan's account. When this message is there, Thomas didn't do that. Instead, what he does is he take this plain text message again. He takes this particular plain text message and he runs a hashing algorithm on that. He creates his own message digest. And he compares this message digest with this message digest. He compares this with it. It compares. That means it is 10 lakh only. Data integrity is achieved. And the symmetric key is used on this message so that the confidentiality is achieved. When the plain text is hashed, he created a new message digest which is compared with the old message digest which is sent by Sam, and it compares very well. That means the data integrity is achieved. He cannot say, I didn't say 10 lakh, I said only 10 rupee or 100 rupee. Now the digital signature. After transferring this, again, Sam can say that I didn't send this message. Still at this point of time, Sam can deny that I didn't send this message. So he repudiate. Maybe he will say he will lie. So how do we prove it? If he lies, how we can prove? Thomas takes this particular digital signature. He runs the digital signature. If you see, the digital signature has been created using the private key of Sam. Sam has created a message digest. It's a chunk of data that has been used, and he used his own private key on top of that. He created a digital signature. That digital signature is here with the Thomas now, and he runs the opposite key of private key of Sam. That's a public key of Sam, which is available with public key of Sam is publicly available, and that public key is applying on this public key of Sam. And once you apply this public key of Sam, if it is encrypting, the very fact that it is getting decrypted, when it is getting decrypted, the very fact that it is getting decrypted itself proves that it could have been created only by Sam, nobody else in this world, because the opposite key of the public key of Sam is the private key of Sam. That will be there only with this particular person, and hence he cannot repudiate. This is where we achieve the non-repudiation. Even after that, Sam is denying. That means the Thomas can take the digital signature and he can go to the court of law. In front of the judge, he can use the public key of Sam. It will get decrypted. You get the message digest. This is immaterial what you get, but the fact that the public key, when it is applied on the digital signature, it is getting decrypted. That fact says that this could have been created by only the person who holds the private key, and here the person who holds the private key is Sam. So he cannot repudiate, where the non-repudiation achieved. So under the public key cryptography, confidentiality is achieved. Confidentiality is achieved by encryption, and the authentication is achieved by digital signature. and the data integrity is achieved by the hashing or a message digest, comparing the message digest, and the non-repudiation is again achieved by the digital signature. This is what the full range of security services given by the public key crypto system. Thank you.